professor. She's been a constant source of new ideas and problems, just very brimming with just a lot of ideas. It's been a real pleasure to work with her. So I look forward to her talk with a very catchy title.
Thank you so much, Eddie, for the introduction and for the invitation to give a talk in this wonderful workshop. I'm going to talk about learning what works best when. And I'm basically going to talk about two styles of two works. One of them is more on the theoretical side and one is more computational. And the first part of my talk is going to be joint work with my PhD thesis advisors, Michelle Gomez and Patrick Jaillet. And the second part of the talk, I'm going to talk about joint work with Ian Dunning and John Silberholz, which we did while we were students at MIT. And currently, Ian is at DeepMind, and John is an assistant professor at Ross School of Business. I'm going to talk about three fundamental questions in this talk. One is, how do you compute projections? So what do I mean by that? If I give you a point outside a decision set or a polytope, then what's the point inside this body that makes the most sense, which is the closest? The distances here need not be just straight line distances or Euclidean distances, but might come from minimizing convex functions, which are more general than minimizing squared Euclidean distance. The second question is going to be, how far can I move? Given a point in a polytope and a direction, how far can I move along this direction while still remaining feasible? The polytopes we are going to consider will have an exponential number of hyperplanes, which makes this problem computationally more challenging. And the third question, that's going to be the second part of the talk, is going to be about, can we learn which algorithm or heuristic works best on an unseen instance of data? Okay, so without much delay, let me go on to the first question of how do you compute projections. Now, the problem of computing projections is important because it arises as a key step in many algorithms across online learning, game theory, machine learning, stochastic, and robust optimization. And in the next few slides, we're going to focus on the problem setup of online learning very briefly, look at an example problem, and then look at this particular algorithm of online mirror descent and see where projection arises as a sub-problem. So all of these algorithms around us are constantly looking at some historic data, or they have some prior knowledge, and then they use that knowledge to make some decision. Given that decision, they observe some feedback from the environment or the users, which are these losses or gains in the dynamic environment, and they repeat this process over time to improve their learning and achieve some goal of maybe showing the best recommendations to users or showing paths with the least amount of congestion to people who are traveling in a road network. And the metric of performance in these algorithms is how did we perform compared to the best fixed decision in hindsight. And this is also what is known as the regret of the online learning algorithm. So let's look at an example. For each of these problems, we can model their decisions using some combinatorial structure. So for instance, I could think about pages and assign a ranking to them. Or I could think about objects and assign a permutation to those objects and say that I'm displaying a permutation of these objects. Or in a graph, I could think about ST paths, or I could think about spanning trees. And these decisions can now be modeled in the vector form. So you have some vertices of these polytopes. And the online learning framework says that, OK, so let the decision maker choose a randomized decision, which is a convex hull of these vertices. I'm going to call these vectors as vertices. These are the pure decisions. So I'm allowed to randomize over them. That gives me this convex space. That's the polytope. Then a linear loss function is revealed. So for instance, let's say I'm looking at permutations, and I say, OK, I'm going to play 2, 3, 1, 4. That means that I'm displaying, let's say, page 1 at rank 2, page 2 at rank 3, 3 at 1, and 4 at 4. And given this display, I observe what are the click-through rates of users. So that's like a linear loss function that I've discovered that has been revealed to me. And then the algorithm suffers a loss, which is a linear combination of a dot product of these two vectors. And this simply penalizes if a highly desired page is placed at a later rank, I'll get more loss. Right? So, yes.
This is linear in the probability distribution over the...
Yes. It's linear in the probability distribution over the vertices. And in fact, Yes, so the linearity plays a key role in going from the losses on the vertices to the losses on the probability distributions. Otherwise, you could not.
But you're not assuming any structure on the losses on the vertices. They can be completely independent.
They have to be. So I'm assuming they're linear losses.
No, but it's linear in terms of the probability. So it's
Yes. So if it's linear in the vertices, then it is also linear in the marginals. So it's also linear over the convex combination of those. All right. And one of the algorithms that's in a very broad class of first-order optimization methods is that of online mirror descent. This is based on the seminal work of Nemrowski and Newton in 1983, although the online part was often attributed to Zinkovich. And it attains optimal regret in many cases, but it is computationally slow. And the key reason for this is for all of these first-order projection-based methods, the bottleneck arises in if you have a point in your decision set, they will typically do an unconstrained gradient step that takes you out of your decision set, out of your feasible set. And then you have to project this point back and obtain the next iterate or the next probability distribution that you're going to play in this learning setup or in a convex minimization setup. And these projections are often obtained by minimizing a convex function, potentially in each step of the method. So this forms a computational bottleneck. Right? So this is going to be the setup, the outline of the talk. I'm next going to describe the problem setup of projections and then explain our novel algorithm IncFix to compute these projections on a very interesting class of combinatorial polytopes. And then we'll move on to line searches and learning over heuristics and algorithms. Okay? All right. So let's talk about which decision sets am I going to compute these projections on. And the short answer to that is what are known as submodular-based polytopes. If you have not heard of submodularity, you can think about the problem of learning rankings of projections and think about learning over the convex hull, so which is the B of f, that's the base polytope. It's a convex hull of permutations of numbers from 1 to n. And note that this has an exponential number of vertices. In fact, the representation of these polytopes also uses an exponential number of constraints. So let's quickly parse what this is. This is saying that the amount of weight that I'm allowed to raise any subset of elements to, that is x of v summed over E in S, that is constrained by a function value on that subset. This function value f of s has very nice properties that capture diminishing returns. So if you have a set of elements and you add an element to it, the gain you'll get is more if you add to a smaller subset than to a bigger subset not containing that element. Okay, and a different choice of the submodular function f gives you different combinatorial structure. So if you fix f to be the simple expression that's only based on the size of the subset, then you get permutations. If you fix it to something else that is based on the rank of a set of edges, the graphic Metroid rank of a set of edges, then you get spanning trees, and you can essentially play with a lot of variety of the submodular function. Okay. And OK, so now let's look at what are the convex functions we are minimizing. So we are going to minimize what are known as Bregman divergences. And to understand what this expression is, let's look at a convex function omega. So this is called the distance generating function or the mirror map in all of these first order projection-based methods. And what this is saying is what's the gap between omega of x, which is a convex function, minus the first order Taylor approximation at y. So this is the gap of omega x minus what's the lower bound at x based on the first order Taylor approximation at y. And plugging in different values of the omega function, we get different distance like measures, which are squared Euclidean distance, scale divergence, and this is what is known as the Itakura-Saito distance, which is used to measure the similarity between audio speech processing signals. And all of these functions are separable. And so this is what is going to be the setting of convex functions that we consider. We're going to minimize strictly convex and separable functions over submodular-based polytopes. And at this point, one might ask, OK, why do we care about all of these different omega functions, different generating functions? And so the short answer to that is, they get different convergence and regret bounds under different loss settings, different polytopes, and you can just plug in the omega function based on the geometry of the polytope, and that will give you a different rate of convergence in these methods. Okay. So to summarize, we are going to minimize strictly convex separable functions over submodular based polytopes, like the square Euclidean distance over the convex hull of permutations. All right, so now I'm going to give you an algorithm by picture. So here I have a point y that is 1.441 that I want to project onto this base polytope, that's the shaded face. And the way the algorithm works is that I'm going to start with an initial point, which has some nice properties. And starting with that initial point, so that's going to be 0 for me, I'm going to look at the partial derivatives of each of the coordinates. Remember that our function was separable. So the partial derivatives only depend on the value of that coordinate. And in this case, the partial derivatives of xe minus ye are just 0 minus whatever the y coordinate is. This is why I get E2 at minus 4, E1 at minus 1.4, and E3 at minus 1. Okay, and then I look at the elements which have the lowest partial derivative, and I increase that uniformly until the set of elements that have the lowest partial derivative changes. So you see, as I increased E2 to E1, I had some movement in the polytope, and at this point, the set of minimal partial derivatives have changed to E1 and E2. At that point, my direction changes because now the algorithm says, okay, move these two uniformly. And so I move E1 and E2 uniformly. That's a new direction in the polytope until I cannot do that anymore. So if I hit a tight constraint, I fix the elements that I cannot increase anymore. So it's a tight constraint that I've hit here. At that point, I fix E2 because if I increase in the E2 direction, I'm constrained by this face. So I cannot do that anymore. And I continue increasing with the remaining elements. So E1 and E3 are the minimum partial derivative elements now. And I increase those uniformly until I hit the base polytope. And that's the algorithm. It gives an exact projection as long as you can compute a univariate equation in exactly. So for the Euclidean case, that's just subtracting two numbers. And that involves just taking the inverse of the partial derivatives. And so as long as you can do that, it computes an exact projection or exact minimizer of the convex function.
So I missed what's happening between the two levels. So is it a different constraint in the base polytope that's becoming tight?
Yes. Yes. So at this point, when I fixed E2, then this face had become tight. That was one of the constraints. And everything else was not tight at that time. And when I increased E1 and E3, then this constraint became tight. That's the sum of all the elements.
But then do you need to search over all the exponential constraints to find them?
Yes, so that's a very good question. I'm going to come to that. How do you do this efficiently? Yes.
I was going to make sure I understand. So you always stay on the exterior of the polytope. You never move to the interior.
I always stay in the interior of the submodular polytope. So the base polytope is actually just a face of the submodular polytope. That's just saying that the total sum of the value of the elements is equal to the function value on the entire set. I'm always on the relaxed polytope. Good. Okay. So there's some details onto how to do this movement inside the polytope that I've brushed under the rug. That was exactly your question. And I'm going to get to this when we discuss how to do line searches. And line searches means that the second question that I've alluded to, that given a point in the polytope, how far can you move along a direction while staying feasible? And we're going to look at how do we do that next. And using some more properties of structural properties of the minimizers of parametric submodular functions, we can show that this entire thing can be amortized in order n submodular function minimizations. And this result is independent of the structure of the submodular function. So as long as you have only black box access, you do need to compute this minimizer exactly. So there are some, if the algorithms that you're using are pseudo-polynomial or weakly polynomial, then that can increase the running time. And in special cases, though, it's very interesting that IncFix can be speeded up to attain much faster running times. And a special case in that sense is that of cardinality-based functions. So as we saw earlier, the permutations function is cardinality-based. It only depends on the size of the subset that you're selecting. And for this function, I'm going to project some points at random on the base polytope, and I'm going to plot the gap from optimality on this plot, which says how fast IncFix is decreasing in the optimality gap versus Frank-Wolf. And the vanilla Frank-Wolf method is something which is very amenable to convex minimization over submodular polytopes, because it only asks for a linear optimization solution, which can be computed using Edmonds' greedy algorithm. So we are going to compare IncFix to Frank-Wolf. And here you're going to see a gradient view. So you see how the gradients are increasing greedily, as I explained in the algorithm. And here you're going to see how the gap from optimality for IncFix is decreasing quite fast. And Frank-Wolf is still sort of trying to get approximate solutions, and it's getting better over time. Now, this happens for cases where it happens for cardinality-based functions, for certain distributions, but it's interesting that IncFix, since it's an exact method, it can do much better than Frank-Wolf. Okay, so with this, let me move on to the second part, which is line searches. And what do line searches do? So as I said earlier, here we are going to look at the extended polymetroid. So initially, my submodular function, the polytope, was constrained with non-negative variables. But now I can also take negative values. And the question I want to ask is, suppose I am inside these exponential number of hyperplanes. I'm inside the submodular polytope. How far can I move while staying feasible? And it's a subproblem in IncFix, but IncFix only uses positive directions, which was well understood using the method that I'm going to explain next. And also in variants of Frank-Wolf, in the Gareth-Heuristic theorem to decompose a point into its vertices as a convex combination. And it has also been used for other problems like densest subgraphs and minimum ratio problems. And the best known method for this, which was strongly polynomial, used n to the 8th submodular function minimizations. So this was a prohibitively large running time. Nevertheless, it was a polynomial method. And this was given by Nagano in 2011. And just to remind us, the constraints of the submodular polytope look something like this. So the sum of the values on any subset is bounded by the function value. And as I move a point, so as I move along a direction, let's say lambda d from 0, then I just want to figure out what the solution of this equation is, which is, as I move in that direction, d of s, what's the maximum lambda such that this is still positive, right? This is when lambda d will satisfy the submodular constraints. Okay? So what I can do as a thought experiment, for every subset of the ground elements, I can plot a line that just depends on the parameter lambda. As I increase that line, at some point I get negative values, and I continue plotting those for all of the subsets, and I obtain what I'm interested in is this lower envelope of all of these linear functions, right? And I want to find this parameter, this maximum lambda star value, at which my envelope is still positive, right? It doesn't go below 0. And it's very natural to look at the discrete Newton method for parametric line search. What does that do? It just samples at a lambda where I definitely know I am violating at least one constraint. That's easy to pick. You just fix an element and violate the constraint for that. And then I do a submodular function minimization to find out what this set is. That gives me the value of the lower envelope. At that point, I can set that set to 0 and get another value of lambda, and continue this process until I converge to this lambda star. And it was an open question what the number of iterations of this method are for general directions. For positive directions, it's easy to show that it can only be a linear number of iterations and a linear number of breakpoints actually in the lower envelope. And we show a quadratic bound in the number of Newton's iterations, thus getting an order n to the 6 improvement in the running time from the best strongly polynomial known algorithm. So with this, let me move on to the next part, which is, so let me skip over this. This is sort of giving some intuition on the proof. We can come back to this if there's time at the end. And let's move on to what works best when. Okay? So what are we doing here? Initially, we started thinking about online learning problems as problems where I want to learn over a set of rankings, I want to get some feedback, I want to show a better ranking to my users in the next iteration. But now we are going to think about, like a giant sitting which has a large set of ensemble of algorithms, and given any new data instance, I'm just trying to figure out which algorithm to use on that data instance, right? And if I can do that better. So what's happening here is that, okay, you encounter some problem in practice, you find out what is known about that problem, and run sort of the best known heuristic for that setting, right? Like often we have theoretical results that say, okay, if you have low sparsity or low arboricity in Sophia's talk, then you do something like that. Or we saw in Piotr Indrik's talk earlier today that if you have dense clusters, then you do this. If you have sparse clusters, then you do. If you don't have clusters, then you do something else, right? So we want to understand what are the properties of our instances that can help us select which algorithm to work best on. And really, we are trying to move from learning decisions to learning the performance of algorithms. And we started looking, so this is joint work with Ian Dunning and John Silverholz. And we started looking at what happened was that we joined as grad students in the Operations Research Center, and we used to think about, okay, what if we had an integer programming solver that we could run a lot of things on that just generated conjectures for us, and we could just sit and prove those conjectures, right? So this is what we are thinking when when John was faced with running maxcut on very dense graphs because he was trying to do name disambiguation in some Google Scholar references. So we started looking at maxcut, and we were like, okay, what is maxcut? Maxcut is a very famous NP-hard problem, which says that given an edge-weighted graph, I want to partition nodes into two subsets such that the weight of the edges between them is maximized. And it also has an equivalence with the quadratic unconstrained binary optimization problem, which just says that I want to maximize x transpose qx for a given matrix x. That's the quadratic unconstrained binary optimization. And there are a lot of applications, a lot of research. One of the applications also that I found quite interesting was trying to detect dense activity graphs in event networks. So let's say you have some Visa card gets some transaction data, and you're trying to understand if there's a card which has multiple declined transactions from various vendors. You want to quickly detect that card and mark that as a fraud, that fraud is happening on that. So there also one could use maxcut. And there are a lot of heuristics that are used in practice. And really, for these heuristics, computational experiments are the key to understanding what would work best when. And but it's hard to find which heuristic works best because of the standard test bed at the time. So the standard test bed had very few graphs. The maxcut instances had very low density. There were some 128 graphs, 105 graphs in that. And the Cubo matrices had very few that were low density. And it was really hard to find which maxcut heuristic would actually work best for dense graphs. That was what we started with. Okay. And further, okay, so this was the problem that we faced. And further, when we looked at a large number of papers, so this is 95 papers which were highly cited in maxcut heuristics literature, we realized that only 10% of the papers used same runtime limits or the same hardware. So it's very difficult to compare heuristics if they are running on two different hardwares or they're running for different runtime limits, right? Then you have no idea which would work best.
Go back to the previous slide. I just was trying to understand all the dots.
Yes.
On the left, the maxcut instances. I thought you were trying this on dense graphs, but then all the dots are low down on density.
Right, so we couldn't find which maxcut heuristic would work in this area, right? The standard test bed only had very low density graphs. case. And the standard test bed for Cubo only had these data instances, so it didn't have any sparse density graphs, sparse densely matrices. Okay. And further previous heuristics. So the number of previous heuristics that compared against 10 papers is less than 5. Mostly they compare against 1 paper, and so that's sort of the histogram, right? Okay, and so we said, okay, you know what we're going to do? We're going to expand the standard test bed. We're going to look at what are the popular max cut heuristics. We're going to run everything on the cloud. So this is just a table of contents from the paper that I put in here. And then we're going to go to more interesting questions that we can ask with all of this data that we've collected. Okay? So let's look at the expanded instance library. So here we thought of, okay, how do we get a large variety of graphs that make this an interesting problem? And we collected heterogeneous instances from, there are some other known libraries for NP-hard problems, like TSPlib, SteinLib. Dimax are the set of challenges. They have a set of challenges. They have various US road networks for different states and cities. We took all of them in. We used a lot of network science generators like Erdos-Renyi, Newman-Watts-Strogatz, Barbar-C-Albert. We used a bunch of those. We then cross-producted that with a bunch of weights from different probability distributions. We constructed like almost more than 3,000, like 3,000 to 3,300 graphs. And that's the coverage of the space for the new instances. So this is the max cut instances in the original graph. These are the cuboid flipped, and then the gray dots are the ones that we expanded our library to. Okay, and this is just displayed on different axes. Okay. And then we said, okay, so these are sort of the properties that we varied to get all of these instances. There are some global metrics like first and second eigenvalues of the Laplacian, chromatic number, and then there are a large number of local metrics that look at the clustering coefficient of the vertices, the average neighbor degree, the core of the graph, the assortivity, which is correlation between the degrees of two neighboring vertices, and so on. And our criterion was that we only want features of graphs that are fast to compute. And I'm going to get to that later in the talk. Why is that important? And then we said, okay, you know, it looks nice. It passes the eyeball test that we've covered a lot of the space. But can we actually formally define a coverage metric that says that, okay, if I look at a particular feature of the graph, and I assign a small 0.05 epsilon interval around it, and I just plot the number of graphs that I have from 0 to 1, then I get something like this. So these are all our 58 metrics, and this is what the standard test bed covered, and this is what we covered in the end. So standard test bed was not too bad. It still had a wide coverage of a lot of the metrics, but then we could get almost complete coverage for all of these metrics that we considered. All right, the next step was the large-scale evaluation on Amazon EC2 cloud and implementation of heuristics. So we did what was expected, right? We did a thorough literature review. We got some 810 papers. We selected 95 with new heuristics. We implemented 37 of those heuristics so that we didn't have to import external solvers. We didn't have to solve SDPs from these 19 highly cited papers. And then we sort of standardized the code base, and we said, okay, you know, they should use similar data structures. They should use shared swap algorithms and so on. And we also didn't want to do any parameter tuning. So we sort of took the parameters that were published in various papers, or we tried to get around that. We enveloped algorithms into random restarts so that they're competitive with the deterministic ones. And then we ran everything on EC2. We selected the runtime heuristic, the runtime limit up front. So we said, okay, for a given graph, what's the time taken to generate 15,000 random solutions? And what's the time taken to do one swap? So the max cut heuristic uses the swap metric, right? So you take a cut, and you just move one vertex, and you figure out which is the best vertex to move to the complement of the cut. And we just computed so we standardized the runtimes with respect to this process. And any new heuristic now takes around 20 CPO days, and it's like $32 to test a new heuristic in this setup. All of this code is available on a GitHub library, so it's all open source, and you can all feel free to play with it. And okay, so we did all of this implementation, and we ran all of this on the cloud, and now we could actually ask some interesting questions. We realized that actually no heuristic dominated on all the instances, which was very interesting. In the standard test bed, it seemed like some heuristics were not doing too well. For instance, there's GLS, so this is genetic algorithm with local search heuristic of Merz and Freiselben in 1999. It was strictly best on no instance in the standard test bed, but was strictly best on 6.97% instances in the expanded test bed. So that just shows that you cannot write off any heuristic without extensively testing it. And no heuristic matched the best performance on more than 22.9% of the test bed. So this was also an interesting point, that I could not just select one heuristic and say that that's the best heuristic for max cut instances. I actually need to look at in different areas of the instance space which is working the best, and then sort of make a big algorithmic portfolio with those. And we'll get to that. Okay, and this is sort of the ranking, which is interesting. This is the average rank. So these ranks are from 1 to 37, averaged over all the interesting instances in our data set. The non-interesting instances are the ones that are just solved to optimality by each heuristic, so we just threw them out. And we looked at deviation from the best solution, what are the instances with the top performance, and so on. By the way, the top heuristic here is Buehrer, 2002. That's based on a rank 2 approximation of the Gomans-Williamson algorithm. So that's quite interesting that it performed that well. And okay, so the question is, can we predict which heuristic would work best on an unseen data instance? And when we asked this question, then we faced a lot of skepticism that these are NP-hard problems, and these are heuristics, you can't really prove anything about them. So the fact that you're trying to learn how well they perform with respect to properties of instances, that seems like it'll not give you any promising results. And we looked further into this literature, and Rice in 1976 already said that the algorithmic selection problem, which is this problem we're talking about, is to really learn the mapping from instance features to the best algorithm to run on an instance, right? For every instance, if I could just learn one number which said how hard is this instance for a heuristic, then I could predict what the performance of that heuristic would be. And so it's really key to get to those set of features that are representative of the hardness of the instance. And when we selected these heuristics, these features, and we asked that how well do we cover these feature values, then a lot of these features have also come from various studies, like phase transition studies that say that, okay, if the density of the graph is less than so and so, and then any random solution is going to be so much approximate to the optimal one. If the density is more than that, any random solution is going to be something which is not that good, right? So people have done a lot of phase transition studies or landscape analysis to understand what are these. So these studies focus on one property, one feature, and ask something about the hardness of they ask, okay, how good would a random solution be? Or how good can a greedy algorithm be for these kind of instances? And so these properties are sort of taking a lot from these studies as well. And here's what we found. So we wanted to have some interpretable heuristic performance models that told us that, okay, if the properties of the graph are in these buckets, then the heuristic is going to perform well or not. And for all of the 37 heuristics, we trained cart models to give us a diagram like that. So the depth was restricted to, I think, 3 or 4 variables. And what this is saying is, okay, if there is this MIS property, which is less than 0.3422, then it's basically giving me the cuts in the space that tell me whether this heuristic performs good or not. And what it's predicting is its rank out of the 1 to 37 heuristics. And here what you see is the red dots are where it achieved close to 37th rank. Blue dots are where it achieved close to 1 rank. And there's a clear sort of an area where this heuristic actually does perform pretty well compared to all of the rest 37 heuristics. Now, this MIS is an interesting feature that we added into our set of features. It just computes what's the approximate maximum independent set. Right? And it seems like somehow that has a very high predictive property for these for predicting what is the heuristic performance. For us, it was like, okay, can we ask the other NP-hard problem what it thinks about this instance? And that's sort of what we're trying to capture with the maximum independent set, which is like just a greedy answer to that. Okay, and so with these cart models, now one can ask a lot of conjectures. One can ask if, why is the case that if the independent set, a greedy independent set in the graph is more than 0.3422, then this heuristic actually performs pretty well. It gets close to the best solution. The numbers that you see in the notes are the rank that is predicted by the cart model. Okay. And now if 2 heuristics have the same variables that the cart model split on, then you can also look at, okay, so it seems that this heuristic, for the same instances, when does one heuristic perform well? So it can be used to compare performance in different regimes. And further, what we did was we bucketed these heuristics into styles of the algorithms. So let's say we took one which was just evolutionary algorithms. So all of evolutionary algorithms went into that bucket. All of taboo search algorithms went into this bucket. And we asked, okay, where do this ensemble of heuristics have the best performance? And so this is basically saying that taboo search does not perform well for low density graphs, but it performs very well for high density. And here it's more complex. And again, it begs a question like, why is this the case? And how can we explain this behavior that we observe in this analysis? All right. And the last part was that, okay, now we have all of this data. We have 37 heuristics. We have the way these heuristics have performed, the way the solution has progressed. For let's say, I think close to 3,000 graphs. And then can we actually just look at the features of these instances and select a heuristic that will perform supposedly the best given those features? And we trained a random forest model for each heuristic that spit out a probability that this heuristic is going to perform the best on this instance. And then we selected the heuristic which has the highest predicted probability. And of course, so we had a runtime budget for each of the instances. We allocated a part of it to compute the features, select a heuristic, and ran that heuristic for the remaining time. And this increased the probability of obtaining the best solution from 15% to 37. The 15% is if you selected a single best heuristic. This was the Bureau 2002. But by doing this switching of heuristics and selection using the random forest, we could increase that to 37%. And the average deviation from the best solution, so this is not the exact best solution because we don't know what the best solution is. We didn't solve the exact problems, but this is the best solution that was obtained by any of the heuristics that we had. So that decreased to 0.09%. And then we said, okay, what if we select a set of heuristics and we let them run in parallel for the allocated amount of time? And at that point, we realized that 48% of the times we can actually achieve the best solution. So with that, I think I'm done. Thank you, and I'm happy to take any questions.
Do you have any, with this work, it seemed to suggest that you could turn it around into a way of generating hard instances?
Yes, so there's a lot of studies where people try to generate hard instances by using evolutionary algorithms and evolving an instance and then seeing if swapping some pairs have a high likelihood of generating hard instances or not. What we did was we didn't want to get into all of that, but we said, okay, we're going to run an instance on, we're going to run all the heuristics on an instance, and we're going to see if all of the heuristics achieve the same answer, then it's probably easy. And then we threw away all of those. So we did a trimming, but it's hard to say whether it was hard for every heuristic or whether it was simple for every heuristic. But basically, because there was no difference in the performance, we just threw them out.
Could you, I don't know if this is possible for MaxCut, but I know for like SAT solvers and stuff, they try to do this kind of, you look over all possible combinations of a subset of variables that kind of breaks down the problem into independent subparts, that maybe each of your heuristics can solve those independent
Right, so we didn't do any of that. There are also studies that switch heuristics. So at some point in the runtime, they're going to stop and they're going to switch a heuristic if you don't get any improvement. We also didn't do that. We just did like select one heuristic and run it for the entire time.
Is there a reason to not do it in MaxCut, or is just
No,
something?
we just didn't. Yes?
Did you try running feature space and see if the statistics for hyper-heuristic drop down a lot? If you say 30 out of 60?
Yes, so I think what you're asking me is like, what was the importance of these different features, right? So I think this is the table we're looking for. This is the mean decrease in the Gini coefficients in the random forest models if you added a feature. So some of these features were actually, they were not useful at all, so you could just drop them. But some of the features, so there are some top 10 features here, up to here, I think, which are pretty significant in the prediction.
Any more questions? All right, let's thank Swati.